Hello everyone, welcome to debjitdecodes. So in this video, we are going to see the Prim's algorithm. And this is one such algorithm which is again used to construct the MST. In the previous two videos, we have talked about what is MST and how we can form an MST using the Kruskal's algorithm, right? So here we will be seeing what is the Prim's algorithm, how we can solve this graph and find out the MST using the using the Prim's algorithm, as well as we will be comparing Kruskal and Prim, both of the algorithms between the approaches, right? So before going straight into the solving this problem or before seeing the algorithm, that is step-by-step procedure to solve this Prim, I would like to start with this point rather. So if you have watched the previous video, you will be knowing that how Kruskal works, right? And if you haven't watched that yet, I would recommend you to go and watch that first. It will be easy to connect for this video. Okay, so let us just start. So if this was the graph given, then what we were doing for the Kruskal? First of all, I have taken the same graph as I have used in the previous video to solve the Kruskal's algorithm. Just a little bit modification is there. That is, I have kind of taken this edge, that is the 25 weight edge between D and E, this one, and I have used a self loop between the node F. So what is the meaning of self loop? Self loop means nothing, that a node is having a particular road to itself, right? And what is the meaning of parallel edge? Parallel edge means there are two edges possible or multiple edges possible from one node to another node. That is what? From reaching to D to E, you can take, there are two options. You can take either the road with 11 kilometers or 11 units of say travel distance, or you can take the 25 units of travel distance. So if any graph at the initial stage has any parallel edge or self loop, it can be there, right? It is true for Kruskal as well. Even though in the Kruskal's video, I haven't shown you these two things, but it is applicable for Kruskal as well. That whenever we will be seeing a graph with parallel edge or self loop, we will be simply trying to remove the parallel edge as well as the self loop. So from here, which edge should we remove? We are selecting what? We are selecting the MST, that is minimum spanning tree. So if we can travel from D to E and the distances are 11 and 25 and our target is to find the minimum path, so we should remove what? We should remove the edge with the maximum weight. So we remove this edge. So whenever there is a self loop or parallel edge, we simply remove that. So there is a self loop here, so we'll be simply removing this thing, right? Same thing, if the Kruskal was having the same thing, we do the same for Kruskal as well, right? So if you can see, now we have the graph what we have used for the Kruskal. Now what is the difference between Kruskal and Prim's, or rather what we were doing in Kruskal's video? Whenever the graph was given, we were picking up the edges and we were sorting that up in ascending order, right? So what we were doing, what is the smallest edge? So we are picking this HG. We are picking this HG. Suppose we are doing like this. There is H and there is G. So it was 3. Then we are picking the next smallest edge. Suppose this one, C and I. So we are picking C and I. This is having 4. So you can see what was the main intention in Kruskal's? We were going edge-wise, right? We are going the global edge-wise, that we are picking the edges globally and we are picking the minimum weight edge again and again and again, and we are trying to see whether the cycle is formed. If the cycle is not formed, then we are doing it repeatedly until there are n-1 edges. That's what we have done for say Kruskal's, right? This was the approach. Now if you can see here, if you can see according to this diagram, what is that? That though the tree is getting formed, but it is not always connected. This is it. This is one component. This is another component. So there are so many disconnected components might be possible in terms of Kruskal, right? But here, if you can see, for Prim's, it is not possible. Why it is not possible, or what is the approach? First, I talked about the Kruskal's approach so that you get a clarity between the understanding between the say Prim's versus Kruskal. So what is the thing we'll be doing? Now let us see the algorithm, that what this particular Prim's algorithm is saying. See, it is saying start from any node. So in case of Kruskal, there was a barrier that you need to pick the minimum weighted edge first. But here it is saying start from any node. So mostly the Prim's is working on node basis. though the Kruskal was working on the global age basis, right? So we are starting from any node. We can start from anywhere, anywhere. It's not that we need to always start from A. We can start from C, we can start from E, we can start from I, anywhere, right? Next is pick the smallest edge connected to the tree. So suppose we have picked this E. We have picked this E. Now you might think that A is having a least weight 6, B is having a least weight 10, C is 4, H is having 3. But if we pick E, there is only two options possible, 11 and 12. Right? So if we start with E, there might be some problem. You might think like that in your mind. Right? But as it is saying that you can start from any node, so you can start definitely from E. But there are two edges coming out of E, that is 11 and 12. So if you pick E, you need to have a bigger edge weight at the first. But your brain is thinking might be there are so many small edges, why we are picking 11 and 12 first? Because if you see, as per the property of MST, this E node will always be there. Because what is the property of MST? That all the nodes from the graphs will be there. And if there are n nodes, there will be n minus 1 edges in the tree, in the MS tree. So E will by default be there. And to make sure E is there in the tree, you need to either take this one or this one at the end. Because if you see in the Kruskal's video, this edge was there. Though we have took it at the very last stage, but this was there. Because any one of these two edge has to be there to make sure that E is there. Right? So we can start with E and we can simply take this edge. Because what it is saying, start from any node. So we can start from any node and pick the smallest edge connected to the tree. So if this node is selected, what we will do next? We will be taking the smallest edge. What is the smallest edge connected to E? This one, DE. Right? Then add a new vertex. So we have now DE, suppose. So we'll be trying to what? Do what? It is not random. Now we have DE. Now we need to make sure that the tree is connected. As I have said, in case of Kruskals, the tree was not connected always. It was several components are there. But here, if you have taken E and D, we need to make sure that the next edge you are going to take either is going to come out from D or it is going to come out from E. So here in Prims, the tree is always connected. So if you have taken this one, ED, the next one you should pick either EF or DF or DC to make sure that the tree is staying connected. So which one will you pick? If you have the option of 9, 16 and 12, you will be picking the smallest one, 9. So up to which part you need to do it? Repeat until all vertices are covered. So you'll be doing this thing until all the vertices are included in your MST, in your final MST, right? So let us just start. Suppose say I am starting with the vertex I. Let us start with the vertex I. So this is my starting vertex, right? Now what will I do? I have started with any node. So what is any node? I have started with I. Okay, this is the starting vertex. Now pick the smallest edge connected to the tree. Now this is the tree. There is only one node. This is also a tree, right? So what we will do? We will pick the smallest edge connected to the tree. What is the smallest edge connected to the tree? There are three edges coming out of I. This one, and this one. So we have three options. 1, 2 and 3. So which one should we pick? The smallest one, right? So what is picked? C is being picked. C is being picked. And what is the value? The value is 4. This value is picked. 4. Right? Now whenever we have reached C, now this is the tree. Now this is the tree. Now what we will do? Pick the smallest edge from the pick the smallest edge connected to tree. Now this is the tree. What is the smallest edge connected to tree? Okay, this is what we need to see now, that from either from C or from I. So what are the remaining edges from I? 8 and 9. What are the values from C? C is having 6, C is having 10, C is having 9. So we need to see between this 10, 9, 9, 8 and 6. So which is the smallest? This 6 is the smallest, right? We are seeing what? We are seeing the edges that are associated in this tree. What are the nodes associated in this C and I? And what are the edges coming out of this C? 10, 9 and 6. This 4 is already there. So 10, 9 and 6. And what are the edges that are remaining from I? 9 and 8. So between 9, 8, 6, 9, 10, what is the smallest one? This one. So we are taking simply this one. We are taking simply this one. This is F and this is 6. This is 6. So this one is picked. Now we have a new node in our tree. So we'll be seeing what? We'll be seeing that what are the edges that are connected to C, I and F, which are remaining, which are not included. These are included, which are not included, and which is the smallest. Now if you see, From F, there is 12, there is 16, this 6 is already included, there is 4. And the remaining one were 8, 9, 9, 10. So what is the smallest? This 4 is the smallest. Right? So what are the comparison we are trying to make between this 4, this 12? What are the ages coming out of F? 12, 16, 6 is already there, and the C is remaining with 9 and 10, and I is remaining with 9 and 10. We need to consider all the things which are not included from these 3 nodes. What is the smallest? Smallest is the 4. So we simply include it. It is G and it is 4. Now we have this tree. So what is the next process? We need to make sure that we also check along with this one. I'm just putting a small sign over here. So we need to check between this one, whatever the nodes is getting included, whatever the ages is getting included, I'm just kind of marking a round sign. This is included, this is included, this is included, just for clarity purpose. And which are kind of we need to consider in the next stage, I'm just giving a small mark like this. So now what are the things? From G, there is 3, 4 is already there, and 8 we have already kind of taking into consideration. So we need to pick between 3, 8, 9, 10, 9, 16 and 12. What is the smallest? This is the smallest. So we pick this one. So we simply pick this one. This is H and this is 3. 3 is being picked. Now H is there. So what are the ages associated? 10, 13, 9, 8, 10, 9, 12, 16, like that. Right? Now what should we do? What should we do next? We should do that this particular thing. If you see now, which is the smallest one between all the marks that has been done? 10, 13, 10, 9, 11, 16, 12, 8 and 9. What is the smallest? This 8 is the smallest. But if you want to put 8, this particular age, what it is doing? It is kind of creating a cycle. But as I have said in terms of MST, because it is a tree and tree cannot have any cycle, right? So if you put this age, this particular thing is being a cycle, right? So you cannot take this one. You cannot take this one, right? So what is the next one? You can either take this 9 or this 9. So simply take, say, this one, the above one. This one, D, and it is 9. It is 9. So this 9 is getting included. Now from D also we need to consider this one. Okay, because from the D, what are the ages coming out? 16, 11 and 9 is already there. Okay, so we need to consider this 11. So what is the next smallest? What is the next smallest? You can see there is another 9. There is another 9. This one, I and H. If you want to put this, again this forms a cycle. Again this forms a cycle. So you cannot put this one as well. You cannot put this one. Are you getting my point? Why you cannot put this one? Now what is the next node? What is the next node you need to choose, or what is the next age you need to choose? 9 is done. So the next value is this 10 or this 10. You can either pick this one or this one. Suppose say I am picking this one. I am picking this one. What is the value? A, and this is 10. This is 10. We have picked this 10. If we have picked this 10, we need to consider this as well, because it is coming out from A, because A is now included in the tree. So what is the next value? What is the smallest value between all these things? 6 is the smallest. So we take this one. We take this one because now we can consider 6 because A is already included. So we consider this one, and this is not forming any cycle. So we are simply considering this one. Right? So see how many ages are there? 1, 2, 3, 4, 5, 6, 7. So what is that? There are total 9 nodes. 1, 2, 3, 4, 5, 6, 7, 8. So only this E is remaining. And there are total 8 ages. There are total 8 ages. So there should be total 8 ages. But how many ages are there? 3, 3, 6, 3, 3, 6 and 2. Right? So if you can see how many ages are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So there should be total 8 ages. So how many ages are there? 1, 2, 3, 4, 5, 6, 7. There are 7 ages. And one node is yet to be included. Now, if you see from the whole graph, then what is the smallest after 10? Because if you want to include this one, because 10 is the smallest value remaining, if you want to include this one, but it forms a cycle. If you can see, it forms a cycle. So this 10 cannot be included. What is the next value that can be included? The remaining values are 13. These are discarded. 13, 16, 11 and 12. So 11 is the smallest value. And if you include this, it is not forming any cycle, right? So it is E and it is 11. Now if you can check how many nodes are there, 1, 2, 3, 4, 5, 6, 7, 8, 9. Here also 9 nodes. So all the nodes are included. First thing is done, because it is saying repeat until all vertices are covered or all the nodes are included. Now let's see whether the MST property is satisfied. What is the MST property? We have said that if there are n nodes, there will be n minus 1 edges. So how many edges are there? There are 9 nodes. So 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 edges. So it satisfies all the property of MST, and there is no cycle. There is no cycle in this particular tree. So this is the final MST using the Prim's algorithm for this graph. I hope it is clear, right? Now let us have the summation. That what is the sum of the MST? What is the value of the MST? If you can sum it up, what is this? 6 plus 10, 16, 16 plus 3, 19, 23, 27, 33, 42, 53. So what is the sum of the MST? 53. So if you can check, if you have checked the last video using the Kruskals, the value of the MST for this one was 53. And for the same graph, the value for MST using the Prims is also 53. Right? So that's the approach for this particular Prim's algorithm. So what is the major difference between Kruskal and Prims? The major difference between Kruskal and Prims is Kruskal was selecting the edges globally and you are picking the minimum weight. Right? But here what it is doing? It is selecting a particular node, then it is forming the tree, and it doesn't disconnect. It doesn't create a tree that here there is one node, here there is one node. It doesn't create components like this, what Kruskal was doing. But Prims always makes sure that the tree stays connected throughout, right? This Kruskal was working with edges, but this Prim is working with nodes. So this is the major difference between Prims and Kruskals. So I hope whatever I have talked about in this video is absolutely clear to you all, and you have understood how the Prim is working. So thank you for watching and stay tuned for the next video.